So today we're going to discuss the third section of our unit on chemical composition and talk about what's called molar mass. Now, molar mass is very similar to atomic mass, but sometimes we want to apply these ideas to molecules, not just atoms, because there's a lot more molecules around than there are atoms. And so we can take the mole and Avogadro's number and apply it to molecules. And so let's take an example. We have CH4, which is called methane. Okay, it's a molecule because we've got more than one atom put together. And if you take a look at the way the chemical formula is written, CH4, this means that there is one atom of carbon and 4 atoms of hydrogen. Because remember, we can look at the subscripts to find out the quantity, and if the subscript is 1, we don't write it. Well, we can equate these atoms to the number of moles, because remember, moles is just representing 6.022 times 10 to the 23rd units. And so it's basically a ratio. For every 1 unit of carbon, there are 4 units of hydrogen. And so we can say atoms within 1 molecule, but if we have a whole bunch of molecules, for every 1 mole of carbon, there are 4 moles of hydrogen. And so it's basically a ratio. Okay, so to find molar mass is similar to atomic mass, only we want to find the mass of a molecule. And so what we have to do is take all the masses of the elements and add them up. And so we sum the masses of all the moles of carbon and hydrogen. Since we said there was 1 mole of carbon and 4 moles of hydrogen, we can use those moles and the atomic masses from the periodic table, because those are in grams per mole, to get grams. Okay, so let's take CH4. We know for every 1 CH4 there's 1 mole of carbon. If I look at the periodic table, 1 mole of carbon is equal to 12.01 grams. If I look at the periodic table for hydrogen, 1 mole of hydrogen is equal to 1.008 grams. And so for CH4, we have 1 mole of carbon times its mass. So technically this should be 1 mole. And the molar mass, or atomic mass, is always grams per mole, plus 4 moles of hydrogen times its atomic mass, which is 1.008 grams per mole. And so if we add all this up, 12 plus 4 times 1.008, we get 16, I believe, 0.04 grams per mole of CH4. Now, because we're basically creating our own conversion factor here, we're just adding up atomic masses, which, if you remember from our rules on significant figures, don't count towards significant figures because they are conversion factors. Molar mass, just round to, maybe the hundredths place or so, and you're good to go. No significant figures here. So, 16.04 is equal to the molar mass, which is the mass in grams of 1 mole of a substance. So basically, we sum the masses of all the component atoms. And so this would be like atomic mass for an atom, only it's molar mass for a molecule. Okay, so try this one on your own. Find the molar mass of sulfur dioxide. Now, here's where all that stuff we talked about with nomenclature and the naming of compounds and being able to write the chemical formula from the name, this is where all that is going to come back, because if I just said sulfur dioxide, you would need to know, okay, that's a type 3, it's 2 nonmetals, the prefix di means 2, and so it's SO2. So all this stuff is going to keep cycling back. Okay, to figure this, or to do the molar mass, make sure you figure out how many moles of each element exists, so use the subscripts, and then use the periodic table to get the the atomic masses for each element and add them up. Okay, you should get this answer, so why don't you pause the video real quick, try this one, and make sure that you're on the right track. If not, keep going with the video, but let's make sure we go over this in class. Okay, so now in the last 3 sections, we've learned about a whole bunch of conversion factors. So let's kind of put them together in order to use them to convert with different units. So the 3 things that we are converting between are mass, moles, and initially we said atoms, but now we're going to widen that to either atoms or molecules. Basically some sort of particle, whatever that is. Alright, well, to go between mass and moles, we need to use either atomic mass, if it's an atom, or molar mass, if it's a molecule. Okay, remember we're finding this information on the periodic table, or we're adding up atomic masses together to get molar mass. To go from moles to atoms or molecules, we're going to use what we talked about in the last section, Avogadro's number. Okay, and that for every atom or molecule is 6.022 times 10 to the 23rd, either atoms or molecules per mole. Okay, and units for atomic mass and molar mass are always going to be grams per mole. Okay, and so since both of these conversion factors have moles in them, moles is kind of like the middleman. And so if you want to go from mass to either atoms or molecules, you have to go to moles first. So we're going to use this flowchart to do a few examples. Okay, first let's find the mass in grams of 4.86 moles of calcium carbonate. Now, first thing we need to do is figure out how to write calcium carbonate. Well, calcium is Ca, it's a 2+. Carbonate from your polyatomic sheet is CO3, 2-, and so we have a 2+ and a 2-. 1-to-1 ratio is good, so calcium carbonate is CaCO3. So we are starting with mass, and we want to go to moles. And so the way that we convert between mass to moles is to use atomic mass, or in this case, because it's a compound, to use molar mass. So let's find the molar mass first, then we'll use it in our conversion. And so for CaCO3, that's a big O, we have 1 calcium, 1 carbon, and 3 oxygens. And so calcium's atomic mass is 40.08, I believe, plus carbon, which is 12.01, plus 3 oxygens, and each of those is equal to 16. And okay, so if we add all that up, we get 100.09 grams per mole of CaCO3. So this is our molar mass. So we're going to use that to go from mass to moles. So we have, I just realized we're going the opposite direction. Whoops, we're going moles to mass, but it's the same conversion factor. So let's start with 4.86 moles of calcium carbonate. Set up our dimensional analysis. We know we want moles on the bottom because we want those mole units to cancel. We know a direct conversion between moles and grams. That's our molar mass. And so we know for every 1 mole of calcium carbonate, there are 100.09 grams. And so if I take my 4.86 times 100.09, and you could divide by 1 if you wanted, that should give me 486.4374. Now if I look back at what I started with, I have 3 significant figures, so I want 3 in my answer. The 4 won't do anything to round the 6, so my answer is 486 grams of calcium carbonate. And it's always a good idea to box your answer or somehow identify it. Okay, let's try another example. So we want to find the number of molecules in 1.56 grams of calcium carbonate. So we're going to go from grams. Now if I want to go to molecules, I know I have to go to moles first, and then I can go to molecules. So to go from grams to moles, I'm going to use, because this is a compound, molar mass. And to go from moles to molecules, I'm going to use Avogadro's number. So let's start with my 1.56 grams of calcium carbonate. Now because I used calcium carbonate in the last example, I already know the molar mass, so I don't have to go through and recalculate that. I want grams on the bottom. Because I'm using molar mass, that's grams per mole, so moles go on top. Okay, it's really important to write all your units out so you know where your numbers are going to go. I know for every 1 mole, there are 100.09 grams of calcium carbonate. Right now, I'm here. I don't want to stop. I want to go all the way to the end of my calculation, then calculate the whole thing at once. So my grams have canceled. I'm left with moles. Now I want to go to molecules, so I know I want moles on the bottom because I know a direct conversion between moles and molecules. And then molecules go on the top. And I know for every 1 mole of calcium carbonate, Avogadro's number says that there are 6.022 times 10 to the 23rd molecules. So when I put this in my calculator, I'm going to take 1.56. Anything on top gets multiplied, anything on the bottom gets divided. So divided by 100.09, and then times 6.022 times 10 to the 23rd. So if I do all of that, I should get 9.38587 times 10 to the 21. Now if I go back to what I was given in the problem, I have 3 significant figures, so I want 3 in my answer. This 5 will round the 8 up, so 9.39 times 10 to the 21. Don't forget your units, my moles canceled. I'm left with molecules, so molecules of CaCO3. So in a very small amount of grams, 1.56 grams, I have 9.39 times 10 to the 21st molecules, which is a large quantity, but remember, atoms are really small. So this answer makes sense. It's always good to evaluate, make sure your answer makes sense, make sure you have the correct units and the correct significant figures. Okay, let's try another example. Let's find the number of atoms in 1 times 10 to the negative 6 grams of calcium carbonate. Okay, so I'm going to start with grams. I want to go to moles first. I know I have to go to moles. There's no direct conversion between grams and moles. Now, I can go to either atoms or molecules through Avogadro's number. I'm going to go to molecules because technically calcium carbonate is a molecule, and then from there I can go to atoms. And this is a little bit different than what we've talked about, so we'll show it through an example. So let's start with our 1.00 times 10 to the negative 6 grams. I already know the molar mass for calcium carbonate, and that's how I'm going to go from grams to moles. I know for every 1 mole, there are 100.09 grams. I already figured that out in my last 2 examples, so since it's the same compound, I can just use it. I don't need to recalculate. I know in every 1 mole of calcium carbonate, now that I'm going to go to molecules, that there are 6.022 times 10 to the 23rd molecules in 1 mole. Because this is a molecule, I had to go to molecules first. I couldn't just go to atoms because it's not just one atom. So now, if I look at 1 molecule of CaCO3, if I count up the atoms, there's 1 calcium, 1 carbon, and 3 oxygens. And so that gives me 5 atoms. And so now I can calculate by taking 1 times 10 to the negative 6 divided by 100.09 times 6.022 times 10 to the 23rd, and then times 5. Remember, when you're putting scientific notation in your calculator, make sure you put parentheses around it. Okay, if I do all of this, that leaves me with 3.008 times 10 to the 16th atoms in calcium carbonate. And so if I want to round to the correct number of significant figures, I have 3 here. So I want 3. That 8 will round to 0, so 3.01 times 10 to the 16th atoms. Okay, and so that's my answer. That's how many atoms in 1 times 10 to the negative 6 grams. Still a ton of atoms for a very small mass. But remember, atoms are really small. All right, let's look at one more example. I want to find the number of moles of just oxygen in 0.73 grams of calcium carbonate. So I'm going to use calcium carbonate first, and then I'm going to break it up into just the oxygen. So I'm going to start with grams of calcium carbonate. I know that I need to go to moles of calcium carbonate first because that's kind of my only option. If you're ever stuck on a problem, go to moles first, and then hopefully you can figure it out from there. Now that I'm in moles of calcium carbonate, it should be easy to go to moles of oxygen through a ratio. Okay, and we'll show you how to do that. So we're going to take the 0.73 grams of calcium carbonate. Okay, we're going to convert to moles using molar mass. And then here we're going to use what's called a mole ratio. And we'll do more with this later, but this is a good introduction. Okay, so from grams of calcium carbonate, I can go to 1 mole of calcium carbonate through the molar mass. I know that every 1 mole contains 100.09 grams And I want my grams on the bottom so that they will cancel. And then I know in every 1 mole of calcium carbonate, now this is where the ratio comes in. It was kind of like the atoms that we did in the previous example. For every 1 unit of calcium carbonate, there are 3 parts of that whole unit are oxygen. And so we would say for every 1 mole of the entire molecule, there are 3 moles of oxygen. And so my moles of calcium carbonate cancel, my grams cancel, I'm left with moles of oxygen, which is what I wanted. And so if I put this into my calculator, I have 0.73 divided by 100.09 times 3. I'm not doing anything with the ones because they're not influencing, but if, let's say, the 1 was a 2, then I would have to divide by 2. So basically, I'm just kind of ignoring the ones, but if they're not ones, then you put them into your calculator. Okay. But it's not a 2, so let's get rid of that so it's not confusing. Okay, if I do that math, I get 0.02188 moles of oxygen. I have 2 significant figures in the information I started with, so I want 2 in my answer. So 0.022 moles of oxygen in 0.73 grams of calcium carbonate. Okay, so we will go over more of this in class.